Hey, good morning, good afternoon, and good evening. Welcome for joining this webinar tonight, organized by the World Federation of Engineering Organizations, the Young Engineers Future Leaders Committee. I'm Tak, dialing in from Hong Kong. And tonight we are very grateful to be joined by three speakers. That is our President, Professor Dr. José Vieira, also the chairman of the Young Engineers Future Leaders Committee, Firas, and also our speaker on this interesting topic of fulfilling offshore wind potential. That's Peter Thompson, the director of East Asia Energy Business Leader of Arup. So before we start, let me pass the time to Firas, our chairman, to say a few words. Firas.
Good afternoon, everyone. First of all, I would like to thank you for attending this webinar today, which is part of the webinar series Engineering the Future, organized by the Young Engineers Future Leaders Committee of WFEO. As you all know that our committee is working closely with the motivated team of young engineers. We are working voluntarily to acknowledge our committee as a global leader for the young voices of the engineering profession. And we are always aiming to have a sustainable ecosystem and provide support, resources, and platform for young engineers in the WFEO community. Our main theme today, it's in line with our will to help in achieving the UN Sustainable Development Goals. And this is always in line with the general potential and the good work that the different standing committees and policy-making committees of the WFEO are putting on the agenda of 2030. As you all know that our committee have representatives from the different continents. And recently we are working on this theme, and we have provided a series of webinars for young engineers on different SDGs. In the past couple of months, or in basically March 2022, aligning with the theme Build Back Wiser, Engineering the Future, we have organized with WFEO the World Engineering Day Hackathon to encourage the engineering students to work in teams towards a global real-world problem. This was like a competition, and this competition, it was a real competition for a real-world project, and we have different teams that worked on this competition and presented their projects, and finally we have chosen like the top 3. Also, in the same theme, Build Back Wiser, we have arranged to do like something with in collaboration with the different organizations that we're working with. We actually work with international organizations related to UN, like UNFCCC and other organizations. And we have we're always taking the 4th of March as an opportunity to celebrate the impact and the outcomes of engineering for a better world. Basically, I'm trying here to highlight that we are putting all this effort and doing these webinars to address to young engineers in order to put them with all the support and resources, and to create in our committee a platform that will give advice for young engineers for the future. And definitely we will continue in this raising awareness on hot topics which we are facing, basically climate action and climate emergency. And we all know the need for action among the WFEO national members. And we have worked previously in COP26, and we're working in the frame of COP27. And we're expressing a deep concern on the matter of climate emergency. That's a quick brief for our activities, and I would like to also thank our President José for joining today, and our esteemed speaker, Mr. Peter, for allowing his time today and his very wide experience to put it for our young engineers. Thank you very much, Tang.
Okay, thanks Firas. Perhaps if our President José Vieira, would you have a few words that you would like to say before we start the webinar?
Yes, Mr. Chairman, thank you very much. Dear participants, I am pleased to take part in this webinar's opening, and thank you all for your presence. First of all, as the President of WFEO, the World Federation of Engineering Organizations, I shall express my gratitude to the WFEO Young Engineers and Future Leaders Committee and its chair, Firas Diab. Firas conceived this brilliant series of webinars, Engineering the Future, last year. And since then, we have been thrilled to watch it bring more and more attendance and enthusiasm amongst the young engineers community. If you are not familiar with WFEO's work, please visit our site wfeo.org and learn more about our activities, especially our standing committees and our many areas of cooperations with the United Nations, UNESCO, and many other international organizations and agencies. This online event illustrates the relevance of WFEO structure and of international cooperation among engineering institutions and individuals at large. It also demonstrates how useful it is that engineers at the global scale, including young practitioners, can get a chance to learn about very different subjects, even when it is not directly related to their field of expertise. This aligns with the new conception of the engineering profession that WFEO has been starting to reflect and promote, especially in the framework of the 2021 UNESCO Engineering Report, in which WFEO took an important editorial role. As acknowledged in this report, the new generation of engineers must master a global approach to the high stakes of the profession in the context of the climate change emergency and the pressing need to deliver on the United Nations Sustainable Development Goals. Therefore, young engineers shall of course have the right skills, but also shall take an integrated approach to the environmental and ethical aspects of their practice and be aware of what is at stake in the most important fields of engineering. This is especially true for subjects which are transversal to sustainable development, which is of course the case for energy, and in particular, renewable energy technologies. I shall take this opportunity to underline the important work taken by WFEO's Energy Committee under the leadership of Jean-Eudes Moncomble on reviewing the potential of the emerging technologies in this sector. This is for sure one of the most strategic tasks that illustrates the relevance of independent assessments in engineering conducted in the framework of international cooperation between professional institutions and their best experts. I am thus grateful to Mr. Peter Thompson from the Arup group to soon deliver his presentation on the important topic of the offshore wind potential. With its long history in civil engineering innovation, Arup has set a good example of how a global industry can reshape its vision and strategy to align with the need for sustainable infrastructure design and construction. This webinar And its theme is also a good example of how we need the public and private sectors to improve their cooperation. As being at the intersection of those, the international institutions and the international non-governmental organization are key to this objective, which is itself the last, the 17th, but not the least of the SDGs. New methods and technologies that allow to achieve the United Nations 2030 agenda need both governmental action and industrial development. Once again, I cannot stress enough how much the engineering profession, because it is the problem-solving profession in essence, is core to this matter. Please enjoy this webinar and remain active in relation with WFEO's projects and activities. Thank you very much for your attention.
Thank you very much, President Vieira. And once again, a welcome all our audience for joining today, which is one part of the webinar series on engineering the future. Tonight's topic is fulfilling offshore wind potential. It covers 3 SDGs, including 7, 11, and 13 on affordable clean energy, sustainable cities and communities, and also climate action. And for tonight's rundown, we'll first be introduced to this topic by our speaker tonight, and then we'll open for a panel discussion before we close. Tonight's speaker is Peter Thompson. Peter is a director and East Asia energy business leader of Arup, based in Hong Kong. He has more than 34 years of experience in the management of design and implementation of major energy and infrastructure works projects across a wide variety of overseas countries. He focuses on works that lead to positive climate impacts, improved resilience, and net zero solutions. As a professional engineer, he has particular knowledge and expertise for the design and implementation of renewable energy systems, including onshore and offshore wind farms, as well as solar and hydrogen facilities, and is currently involved with advisory services and the detailed design works for a number of projects currently being undertaken in East Asia. So without further ado, may I now pass the time to Peter.
Okay, thank you, Tak, for that introduction. Can you see my screen?
Yes, we can.
Okay, so thank you very much for that, and good morning, good afternoon, and good evening to everyone that's joined this seminar today. As Tak said, my name is Peter Thompson. I'm the East Asia Energy Business Leader for Arup, based in Hong Kong. And my subject today is talking about the fulfilling offshore wind potential. I actually counted 6 SDGs rather than 3, but you know, it's a matter of subjective decision making, really. So I'll start really with just an introduction to Arup very briefly. For those of you that aren't familiar with the company, we're actually a global firm of consulting engineers, designers, planners, advisors, and architects. We have around 16,000 staff. We have 88 offices spread across 33 countries. So we have very good coverage across the globe, and we operate as a global company. We're probably most well known for some of our tall buildings and sort of iconic structures, things like the Sydney Opera House, as well as the Beijing Olympic Stadium and other such projects. So that sort of gives you a flavor of the sort of projects that we get involved with. But energy is a big part of the business now. It's about 10% of our infrastructure business and growing all the time. And it's something that we are passionate about because it deals with sustainability issues in particular. We are one of the leading engineering advisors in the world. You can see here some of the accolades we've received from journals like IJ Global, Infrastructure Journal Global. We pick up awards typically every year for some of the advisory works that we do around the world. And a lot of that's related to energy and in particular offshore wind, as that's really one of the market drivers. Sustainability is at the heart of the company. We were the advisors or sustainability advisors for COP26 last year, fortunately enough. And during that COP seminar, we announced that Arups would no longer support fossil fuels. And therefore, what that means is that we will now focus purely on clean solutions, and offshore wind is obviously a big part of that. So essentially, we use the UN sustainability goals as a means of judging those projects that we believe we should pursue. And if we find that any project that comes to us that doesn't fulfill any one of these goals, then essentially we won't do it. So it really is at the core of the company now, and something that we believe passionately about in order to join that race against time for climate change. So going back to wind, this slide shows a global map of wind speeds around the world. So you can see the color system here, the color key at the bottom or on the side, essentially with wind speeds varying from about 2.5 meters per second up to 10 meters per second. If you're going to develop an offshore wind farm anywhere, typically you really need a wind speed of anything in excess of 7 meters per second. There are some sites that would accept slightly lower, but really if you want to have an economic and a viable case, you really need to be looking in the range of sort of 7 and above. And if you look at, obviously the offshore wind is located in the sea or in the ocean environment, and the Earth is obviously covered by 70% water. So there's enormous potential for offshore wind. If you think about it, if you're able to put offshore wind structures across the whole area, we would have an enormous amount of energy generation system that we can tap into. If you look at the map as well, I think it's very noticeable that most of the high winds are in the northern area of the of the northern hemisphere, and also on the southern part of the southern hemisphere. And typically along the equator, the wind speeds are typically lower. So really, most of the areas where we've started developing offshore wind at the moment are places like Europe, America soon, down in Australia, as well as on the east coast of China and Japan and Korea. These are all areas that are exposed to high winds, and therefore something that is ideal for the generation of offshore wind power. So if we look at that in perspective, obviously we can't develop the whole of the sea area. A lot of it's not practical or commercially viable. So there was an assessment done by ESMAP looking at 115 countries around the world and looking at how much wind power that can be generated from a set number of criteria. And that criteria was to have areas with a wind speed of greater than 7 meters per second above a level of 100 meters, and that's the typical hub height of a wind turbine. They look for fixed-base systems for water depths less than 50 meters. For water depths in excess of 50 meters, but less than 1,000, then floating solutions are obviously a viable solution. But also we'd like to limit the zone to 200 kilometers from shore, and that's really to minimize the amount of electrical cabling from the proposed wind farm to shore, which is obviously a big cost impact. And also the turbine sort of density, it was assumed to have 3 megawatts per kilometer squared for wind speeds between 7 and 8. And for wind speeds higher than 8, we were looking at 4 megawatts per kilometer squared. And if you take all those together and just look at that very small area of sea frontage, you can determine that the total energy potential is around 71,000 gigawatts, which is enormous. It's enough power to provide electricity demand for the whole of the world in its present conditions. So it really is an enormous amount of energy that's there to be ready and waiting to be tapped into. It's just really a matter of working on the technology and the economics to make them more viable. But there is a solution there that gives us some hope, if you like, to completely change our electricity generating system to one of renewables. And offshore wind is particularly relevant to this because it has such a high capacity factor. When you compare it to other forms of renewables like solar and onshore wind, it really does generate significantly more power, and it generates the power en masse as well, which is another important factor. So if you look at where we are, we talked about a figure there of 7,000 gigawatts. Where are we at the moment? We're up to about 48.2 gigawatts of installed wind capacity. And you can see that there's been an acceleration over the last 10 years in the development of offshore wind. So you can see that it's sort of rising exponentially. So that again gives us some hope. If you look at the capacity awarded just this year in 2021 to 22, there's another 50 gigawatts of power that's a wind capacity that's being awarded. in different countries, primarily in China, UK, US, Poland is a new area, but there's obviously some other smaller countries like Taiwan, Denmark, Germany, Japan, all contributing to this journey that we're working on towards a cleaner power. If you look at the expectations over the next 15 years, the expectation is to grow by another 10 times. So by 2035, it's expected that we'll grow from 53 gigawatts in 2021 up to 500 gigawatts by 2035. And if you then project onwards by 30 years, so this is to 2050, the projection is to be up to 1,000 gigawatts of offshore wind. It's still some way short of the 71,000 I mentioned at the beginning, but obviously it's something that will grow over time. But it's still a tremendous amount of power that's being developed, and you can see the areas where most of that growth is occurring, particularly in Asia, particularly around China, Europe, North America. Australasia had some fairly nominal targets until recently, but you can see that there's been new government regulation or in Australia to promote the use of offshore wind. So what's really driving this? You know, we noticed this big exponential jump in offshore wind popularity over the last 10 years, and it's really driven by the changes in technology. You know, if we're being honest, you know, up until the year 2000, you know, we were looking at wind turbines of the order of 0.5, 1.2 or 2 megawatts in size, and really that's not economically comparable to other forms of energy power generation if you look at things like coal. But as the technology's advanced and as the supply chains developed, the wind turbines have become much larger. They're becoming larger year by year. So you can see now that over the last 10 to 15 years, we've gone from 7 to 9. We're now looking at 13 to 15 megawatt machines, and there's even designs for 20 megawatts machines on the drawing board. So it really is growing very fast, and it's really the fact that we have these much larger machines, much more efficient machines, and a supply chain that goes alongside that that's mature, that we're able to get these savings, which makes offshore wind that much more competitive. And that, as I say, it's really driven by those technologies. As you can see, this is a cost breakdown of offshore wind in terms of sort of development costs, capex and opex. The majority of the costs come from the constructions. That's the turbines, the foundations, and the installation accounts for around 30 to 40% of the overall costs. And then you've got operations and maintenance taking up the last sort of 30 to 30% or so of the overall costs. So really, by trimming down those costs of the turbine, reducing the number of foundations, and improving upon the methods of installation, we're really able to make cost savings in the design and construction of these types of technology. So what does that mean in terms of the levelized cost of electricity, which is really the key driver, really, or the key determining point as to whether or not a particular power system is economically viable or not. So this shows a chart of where offshore wind has come from the year 2005, where we were looking at a levelized cost of power of something anywhere between sort of $150 and $100 per megawatt hour. You can see there now in 2020, we're hitting targets of around 99 to about $60 per megawatt hour. And you can see projections there in 2025 to go even lower. And if you compare that against other forms of power, you can see offshore wind here over on the left-hand side in light blue, with a value of between 99 and $65 per megawatt hour. And that compares really favorably now against coal, against PV, against onshore wind. It's cheaper than more traditional open cycle, closed cycle gas turbines. It's even cheaper than nuclear and other sort of more novel means of electricity. And it's really this pricing that price competitiveness that has led to the development of offshore wind across many continents in the world, and we hope it will grow even faster over time. If we project that even further to 2050, you can see that it's starting to level off. We are reaching the sort of point where it's sort of optimized to the maximum, but we still are expecting some savings. So if you look at where we are now, about $88 to $58 per megawatt hour. We're looking to move towards 60 to 36, hopefully at the lower end rather than the higher end. But there's a range of numbers there that will materialize even greater savings over time. So these are the results for United Kingdom. United Kingdom is one of the largest offshore wind farms in the world. So it does have one of the more developed supply chains. And it's really that's what's key to the development of these offshore wind farms, is to develop that local supply chain. And with those supply chain advantages, one can achieve really low costs. So what are the key issues for the development of offshore wind? There's actually a really useful document that we helped produce for the World Bank Group. This was a document that was done by Arup alongside some of our partners. What this essentially looks at, it's a really useful guide if you want to learn more about setting up offshore wind farms. But it looks on sort of 4 basic topics. It looks at strategy, policy, frameworks, and delivery. So if you look at strategy, it talks about what makes for a successful offshore wind strategy. And that's really about having a clear role for the offshore wind in the country's energy mix, a clear role in the economic development plans, and then setting the policy that drives that strategy. And that's about looking at long-term stable targets to give developers that confidence about a strong supply chain development plan. And then setting out the frameworks to achieve that. So what frameworks are needed to enact those policies that I just mentioned? And then lastly, the delivery side. So this is really a worthwhile publication to look at if you have time. So I'll just talk about a few of those points there. So as I mentioned, at strategy and policy, it's about developing that coherent energy and economic strategy to evaluate the potential of offshore wind. The UK has been particularly strong on this. They developed a very clear strategy early on over the last decade that brought together many of the key industry stakeholders. It encouraged the developers to come. It encouraged the supply chain to develop with confidence, and then also the sort of regulatory bodies were on board to promote the idea and push forward with the development of offshore wind. And that's why the UK now has one of the largest offshore wind farms and is just released round 4. So that's another substantial number of wind farms that's coming out, as well as Scotland as well, which also is part of the UK, another large volume of work that's coming through. So they've set these clear targets and also targets not just in volume but also for the levelized costs of energy, so that again the contribution that wind makes to the market is compatible or comparable with other forms. And then frameworks and delivery, and things like this. Investors need the transparent processes to be able to deliver the milestones. So this is looking at things like marine spatial planning, seabed leasing, making it easy for the developers to do so. Looking at environmental permitting, facilitating the licensing of the wind farms, developing consenting processes, health and safety issues, as well as revenue support. Grid connections, obviously, to build a wind farm, you need to have somewhere to connect. So grid connection is somewhere where government intervention can help significantly in promoting the development of offshore wind. Alongside that is also port development. You need construction ports as well as operational ports, and having those to hand is essential, and also developing the supply chain, as I mentioned before. So what is the development process? I just need to get a drink. So before you set out on a offshore wind farm project, there's a number of sort of pre-project development and project management tasks that one needs to do. So usually you start with looking at the development and consenting services. So that's really understanding the local regulatory regime and looking at how the wind farm could fit into that development regime. The second part is to look at site identification and assessment. Obviously, there's a huge area of sea to be looked at, and the first exercise is really to look at the different sites, looking at the water depth, the wind speeds, the distance to ports, distance to the grid, the grid connection points are all sort of key factors that will determine the ultimate LCOE and the competitiveness of a particular wind farm. So that we do have systems in place that allow easy scanning of a whole sort of seabed area to be able to determine the best sites. And that's illustrated by those figures at the top. And then once you've identified your site, the next activity is environmental impact assessments. Obviously, the environment's very important, and offshore wind farms can obviously have quite a big impact on both the seabed as well as mammals and fish, as well as sort of human impacts as well. So the environmental impact is usually one of the first areas of work that's done by the consultants to determine the viability of a particular site. Alongside this, we'll be looking at metocean studies. That's looking at the wave environment, the wind environment, the bathymetry and the currents, all the sort of factors that would impact on the design. We'll be looking at project programming, developing the key program tasks and identifying those risks, and then monitoring them against delays and equipment purchase planning. And then project permitting and licensing, just going through the permitting process of your particular area is obviously a very important point as well. Wind resource monitoring is very important. There are those sort of global maps that I showed you earlier that give an idea of the wind regime across large areas. But really, if you're going to develop a wind farm, you really need to know the local wind regime. It shouldn't be too different from the global sort of mesoscale data, but there's nothing better than having something that's really reliable, that's able to monitor the wind speed at your specific site. And for that, you can have a sort of fixed base monitoring station, or you can have a floating LiDAR system that floats in the water, measuring the wind speed over a period of anything up to a year to 2 years of data. The ground conditions are obviously very important, so you'll be looking at doing some early geotechnical and geophysical assessments. This is usually things like boreholes, CPTs, as well as sort of geophysical methods to determine the ground conditions. And this is something that you would do in stages. So if at the early stages, you might do just a few boreholes, but as you start moving through from concept to detailed design, you'll be looking at doing investigation on every proposed location of the wind turbines. And then, of course, turbine selection is important. You need to understand the type of turbine, the class of turbine that you need, the size of turbine, particularly in places where you've maybe got high seismic or high typhoon risks. You need to be very careful about the choice of turbine, but also it's not just about the technical aspects, it's sometimes about availability, which turbine models are available in particular areas, and which suppliers are able to provide the turbines in the program period that you need. So there's a whole range of different factors that one needs to consider. So once you've sort of identified your site, you then move into the concept and feed design services. And for this, you do an energy yield analysis and micrositing. So this would ascertain the amount of energy that you think you can abstract from the particular site based on your chosen turbine and chosen layout of wind turbine. And you would select the wind turbine orientation based on the direction of wind. And then you would come up with some initial concept and pre-feed designs. This would be looking at what the most suitable foundation might be, whether it's monopiles, jackets, or some other system that would be applicable to that particular site. And this would help with the development of initial cost estimates and facilitate the planning of purchasing the balance of plant equipment. So this slide sort of shows a typical sort of wind farm. This is one that I've sort of grabbed off the internet, but you can see a typical wind farm layout. It really is orientated according to not only the seabed conditions, but also the leasing area, site boundaries. The wind turbine orientation would be pointed towards the direction of best wind. And then you would have the blue area, the blue lines there are the sort of inter-array cables that connect each of the turbines together, which are represented as little dots, and they connect to an offshore substation, which is identified by the red dot in the middle of the zone. And then you've got the export cables, as noted in orange, which take the power that's generated to shore. You'd also have a construction harbour, which would normally be one of the existing harbours, one of the larger harbours that's available with a significant amount of space for the construction of the wind farm. And then once the wind farm is constructed, you would then develop a separate O&M harbour. They're usually much smaller, but they're used to undertake the operations and maintenance of the wind farm when it's constructed. And this just is an illustration of the importance of the wind turbine layout. You'd be looking at sort of separation distances between turbines of something like 10 times the diameter of the wind turbine. And as turbines get bigger, obviously that distance gets bigger. But you can see here the issues with wake effects. And these are the sort of things that one needs to address when doing that energy yield analysis to ensure that the interference is minimized from different wind turbines, and also the output is maximized. Just to show you schematically in section what I was just describing earlier, so you can see the wind turbines out to sea. It's fairly simple. They're connected by the array cables. The array cables connect to the offshore substation. Sometimes you don't need an offshore substation. It really depends on how far you are from shore. If you're within, say, 10 kilometers, then probably you'd take the array cables directly to shore, to the substation connection. If you're sort of more than 20 kilometers offshore, then usually having an offshore substation is more cost effective because of the length of the cables. But in this case, you can see we have the array cables going in, we've got the export cables going out. It goes into the substation on shore and then straight into the grid network. Okay, so the next stage then is really about how you would set up the offshore wind farm. So you'd also do sort of grid connection studies, to understand how the electricity is taken from the wind farm site, how it interconnects with the onshore substations, and then how that electricity can be distributed through the grid. We do some risk assessments. Obviously, it's a lot of money to develop some of these wind farm sites. So you need to be looking at the risk assessments and identifying mitigation measures. And then lastly, the CapEx and OpEx estimates, which is determining the capital costs as well as the operational costs of the potential wind farm. So once you've established all of that, you'll be into and you've got the decision to proceed with an economic case, you'd then move into the installation and commissioning stage. So the first point for this would be to set up a construction port to prepare the laydown areas and establishment of heavy lifting berths for the different pieces of equipment. So that would be the blades, as well as the towers and foundations for each of the wind turbines. Obviously, with so many components and such limited area, usually a lot of these harbours are quite congested. You'd need to have some sort of logistics planning to understand how you move materials in and out and how you store them and stack them within the facility to ensure a smooth and efficient process. And then, of course, you'd move to the installation of the key civil works, and that would include the foundation installation. In the first case, you'd be installing the substations, offshore substations, as well as developing the onshore substations. And then finally, you'll be looking at turbine installation and then the electrical connections in between. So that would be connecting the offshore cables or export cables, including the sort of the routing as well as the burial, as well as the inter-array cables. And then once you've taken or achieved or brought that cabling to shore, you would then look at how the onshore cabling can be taken through the land to the nearest substation, which is not always close to the coast. It can be some kilometers inland. So again, you need to look at permitting and cable laying activities. And then finally, once you've got it all connected up, you'll be looking at the commissioning and testing of the facility. And once you've got your wind farm operational, the next phase is the operations and maintenance. So for this, you'd set up your operations and maintenance port, which, as I mentioned before, will be a smaller port, usually one that's bespoke and dedicated to a particular wind farm or number of wind farms in a particular area. It would comprise usually an office and a warehouse to house the spare parts and tools and equipment that one needs, as well as an operations center to understand the behavior of the wind farm throughout its lifetime. And then you've got the maintenance and service team, so that they'll be looking at blade inspection and repairs, looking at the balance of plant maintenance and repairs as well. So they'll be constantly going out to site, looking at the SCADA data that comes out from the different wind farm components, and then identifying areas where they can provide repairs and maintenance in time before a failure is to occur. And then in the extreme cases, we can also do foundation inspection and repair, but foundations are really designed to be there for 25 years. So they should be robust and not in need of too much repair, but every now and then there are instances where one does need to do so. So hopefully that just gives you a broad overview of the sort of process that developers may follow. If we go into the design office now, just looking at some of the things that we do as a consultancy. So as I mentioned early on, part of the first task for us is really to look at where the best sites are in a particular country. And for this, we developed a digital tool, which we call Scale, which really looks at a whole array of different characteristics of a seabed area, and will determine the levelized cost of energy for each one by looking at the various parameters, and that includes things like water depth, the distance to shore, length of cabling, proximity to ports, even looking at some of the soft constraints as things like environmental considerations and fishermen issues. So it's a very comprehensive tool that we use. We then look at the design of the offshore wind farm, and it's obviously offshore wind farm is much more technically challenging when compared to onshore wind. It's obviously in a much more aggressive environment. It's located under the sea, so a lot of the foundations are installed blind underwater, and there's also subject to quite a number of different loading effects that you wouldn't encounter on shore. So that would be things like hydrodynamic forces. You'd have current and wave loadings, as well as breaking waves and scour to deal with. But alongside that, you've got issues of soil foundation turbine interaction, as well as fatigue type issues, as well as marine growth. So there's a whole number of different areas that one needs to look at as a designer, and this is something that sort of separates many of the larger consultancies from the more routine designers, because it really does need a high level of computing sophistication to design some of these foundations efficiently. If we look at the different types of foundation that one can choose, the most common is the monopile foundation. I think over 70% of the world's foundations to date have been built on monopiles, but there's also a number of other different systems that one can consider, including gravity-based systems, monocaisson systems, multi-pile systems, multi-caisson, and then you move into the sort of floating arena with tension leg platforms and spar, as well as the submersible, the semi-submersible type structure. As I say, most of the wind farms to date have been really built in the shallower areas, so it's monopiles and sort of jacket type foundations are really the main type of foundation that's being done at the moment. So this just gives you an illustration of those types of foundation. Part of the early planning for us is to look at finding the best solution for a particular site. So if you're looking at water depths less than, say, 30 meters, it usually plays towards monopiles. If it's more than 30 meters, you're moving into the area of jackets. And if it gets deeper than say 50 or 60 meters, you're into the arena for floating type systems. I think the other point I'd like to note as well is just as a means of making the designs more efficient. One of the things that our company is doing, and I'm sure some of our competitors are doing the same, is to really try and automate the process. You can see with offshore wind farms, there's a lot of repetition with each of the wind turbine foundations, but they do have slightly different ground conditions or slightly different wave conditions. So it's really an ideal design process that's ideal for automation. So we have developed in our company a whole range of different digital tools to facilitate this, and it's really an automated process, so that rather than looking at clusters of wind farms, we can now look at individual turbines within each of those wind farms, so we can come up with a more optimized and rational design for each one. So for us, we have a system called Optif, and within that that looks at jackets as well as monopile foundations. Okay, so it's really about automating that design process. So this just talks a little bit about Optif. I won't dwell on that one too much. So if we look at the different types of foundations, so monopiles I mentioned are the most popular. They are suitable for areas up to 30 meters of water depth. They're typically 6 meters in diameter, but actually up to more like 11 meters now. With the larger wind turbines that we're looking at the moment, we are looking at sort of 9, 10, 11 meter diameter monopiles now. They're relatively simple to design when compared to some of the other systems, but some of the sort of vibrations and deflections are subject to cyclic loading, and therefore the moments need to be considered quite carefully. there's also issues in terms of the transition piece that and verticality of that transition piece that needs to be considered. But as I mentioned, they are getting bigger. So the larger monopiles, we call them monopiles XL, are sort of getting larger than I've just mentioned. So these are really necessary for the much larger wind turbines, areas where you've got much deeper water or deeper penetration requirements, as well as heavier loads or heavier increased wave loading. So the larger the monopile gets, it's obviously a very simple component, but the larger it gets, the more significant the diameter becomes compared to the size of the waves and the strength of the ground. That requires much more advanced geotechnical engineering in order to determine the springs and the sort of cyclic fatigue effects that one can find. So we are looking at much larger systems now for those sort of monopile foundations. The next tier up is the pre or post pile jackets. There's an illustration here of some jacket foundations. So they're suitable for water depths of sort of anywhere between sort of 20 and 50 meters. There have been some designed now for even greater than 40. So some are pushing the boundaries up towards 60 meters as well. They typically attract lower wave loads compared to monopiles, and that's really because of the open structure. And they're oftentimes, if you're looking at some of the more developing nations, quite an easier option for fabrication, which is available perhaps more locally than say monopiles, which require a high degree of manufacturing expertise. But they are typically higher construction costs, but it really does depend on the nature of the site. They can be cost effective if the water is particularly deep. Suction bucket foundations, this is something we're doing at the moment in Hong Kong. This is really, it's a novel sort of foundation technique that one uses in soft ground. And that's something we have a lot of in Asia. We have thick marine deposits. So it's the sort of solution that we're using for the offshore wind farm here. It allows faster insulation, it allows shallower penetration, it can take large capacities and sort of reduces the amount of installation operations that are required to support the works. Can also lead to significant LCOE savings. There are some novel solutions. This is one of ours, which is the wind system. You know, I think a lot of the cost for the installation of offshore wind farms comes from the support vessels. So one of the things that we tend to look at is how we can minimize the amount of support vessel requirements, which leads to generally greater cost effectiveness. This is just one solution. Another solution is the concrete gravity foundations. Typically this is more expensive, but there are sites, I think, as we start getting deeper and we start getting into areas of hard ground, then I think that concrete gravity foundations could offer a good solution. So this is places like Australia, maybe Korea, those sort of places where you have those hard ground conditions. In terms of the foundation design analysis, there's obviously a number of analyses that one needs to do, looking at ultimate limit strength as well as serviceability limit states. But probably the most fundamental for offshore wind is the fatigue limit state, and that's due to the sort of rotational dynamic effect of the turbines. That if you are not careful, if you don't consider the frequency of the different components, then you can lead to fatigue or additional fatigue in the foundation and tower structures. So this is something we look at very carefully as part of the design. We also look at soil models. I mentioned as the foundations get bigger, there's more need for a more sophisticated soil material models. And so that's sort of stems from the simple model of a linear elastic model all the way through to what we call sunny sand in our LS Dyna 3D analysis, which really looks at the behavior of the soil in a much more detailed manner. We can also undertake advanced analysis and parametric studies. So we're looking at things like grouted flange connections, looking at fatigue assessments and dynamic analysis, looking at the integrated data models, as well as automated design processes, scour assessments using CFD models, as well as looking at things like how you might decommission a particular project at the end of its life. And then there's other effects that we've come across, particularly during the days when we were doing oil and gas. It's a phenomenon called ringing. So it's really an issue if you have very large members in the sea environment. It can lead to these sort of impulsive loads as waves slam against those large structures. It's something that, again, we take care of when we design these very large structures out to sea. And then lastly, as some of these wind farms become quite old, there's many of those in the UK now that have been there for 20 years. They're reaching end of life. These typically they're designed for 25 years. What we do find is that many of the early designs were sort of over designed to some degree, and therefore the amount of fatigue life that they were designed for is much higher than the fatigue life they've actually experienced. So there are ways and means by instrumenting some of these foundations that we're able to extend the asset life by sort of 5 to 10 years of life, which is essentially pure revenue for the developers, and therefore something that's really attractive as a service to maintain the longer or longevity of a particular wind farm at a particular location. And then last but not least, you've got floating concepts. Now, floating is something that's coming out, I think, now. You can see in ScotWind that the latest round in the Scottish offshore wind auctions, I think over half of the sites that were auctioned out are now floating systems. So to me, it's a really exciting time. You can see as the water depths get deeper, you can see that floating systems are going to start to become much more popular. They are quite expensive at the moment, and I think that's really just a function of the fact that they haven't really been produced en masse or on scale. And I think that once they are produced to that level of sort of commercialization, then they'll become a much more attractive or competitive option compared to some of the fixed-based systems. But you need that step to be pushed out into the deeper water in order to really promote the idea of these types of system. And I think the UK government, as well as Europe, are really taking some strong steps to push them forward to get that technology moving forward. As I mentioned, it is quite expensive at the moment. This is just a comparison of the sort of cost of the foundations, comparing monopiles and jackets to the floating systems. They are still quite a bit more expensive than the fixed-based systems, but as I mentioned, with scaling, I think those costs will come down quite rapidly. And then just looking at what's next, what's the future things that are happening in offshore wind. There's a few exciting developments that I'm aware of. We are looking at in the UK at providing those grid connections offshore rather than onshore systems, so that there is noted that it did seem a bit silly that all these offshore wind farms were trying to bring their cables to different points onshore. It would be much more sensible to develop an offshore grid connection so that all the offshore wind farms can connect to a single point, and then that offshore grid connection then can have a single connection back to land, and I think that will have some significant savings. They're also looking at things like energy islands. This is creating artificial islands in the sea for the support of offshore wind farms, again cutting down on those costs. There is some novel ideas for underwater substations, so this would do away with some of the foundation systems that's currently required for the offshore substation structures. And then, of course, there's the possibility of green interconnectors. There are obviously some areas that have more wind resource than others, and the natural idea would be to share some of that green energy with some less fortunate countries that don't have such strong renewables. And you can see a picture in the bottom there is a cable from Australia to Singapore, which is being looked at. It's called the Sun Cable, and it's a possibility of bringing that renewable energy over long distances, and something that I think could be relevant in many countries. And then just the last point here as well is really, to my mind, the future for energy and the decarbonisation of the energy system really hinges on the development of hydrogen. I'm a really strong supporter of the development of a hydrogen economy, and obviously offshore wind plays into this. It's the first part of that program that's able to produce that green energy from renewable power. You can use that renewable power in an electrolysis process to generate hydrogen, and then that hydrogen can be used as an energy storage medium to power a whole range of different end users, and that includes transport, industry, heating, as well as directly for power generation. So, you know, and if you look at the emissions when you burn hydrogen compared to current fossil fuels, it's a world apart. The byproduct of this process is just water, and it's just water basically. So it's a much cleaner system compared to others. So I think that's it really. So hopefully I've given you a quick run through of typical offshore wind practices. I'll be happy to take any questions that you may have.
Yes, thanks very much, Peter, who has given us a very comprehensive approach into the design of a wind farm, and also a little bit of an insight of the future development of these wind farms as well. So we'll open up for questions for this panel. Amongst our panel tonight, we have different engineering backgrounds covering civil, structural, and geotechnical. So we have received some questions, but audience, you can also type in your questions in the chat box, and we'll pick them up and try to address them as we go on. So far, we've received some questions, and let me try to moderate how we can effectively discuss these. I have grouped them into 4 main categories, and let's see if we can have enough time to address them in the next 10 to 15 minutes. So we'll be talking about the feasibility, about achieving net zero. There's also questions on the grid and market stability. Thirdly, there's offshore construction technology, and fourthly, the views or concerns or questions about the cost. So if I may, shall we start by talking about the feasibility in achieving net zero? So the question is, many countries and regions, including Hong Kong, have set their net zero target to be reached by 2050. So is it feasible to achieve this target theoretically by wind energy, or how big a portion of this energy mix can we rely on or allocate to wind energy? So any takers, or perhaps we can let Peter to share with us your insight.
Well, I think it depends where you are and which country. And you mentioned Hong Kong. I mean, I think Hong Kong the solution to net zero can't be purely offshore wind. There is plans for offshore wind farms going on at the moment by both CLP and Hong Kong Electric, but the proportion of power that can be produced by those wind farms is quite small relative to the overall energy demand of the country. And I think I did estimate, if you actually developed every portion of sea area around Hong Kong, I still think you'd only have around 20 or 30% of the energy capacity. So it's not possible in every country, but I think there's certain areas like the UK, Europe, Americas, as well as China, where the amount of power that can be produced by offshore wind can be a significant portion, and it does enable them to turn off some of the less clean forms of energy production at this time. But you know, I'm a great fan. You talk about Hong Kong. I'm a great fan of hydrogen, and I do think that offshore wind, whether it comes from within Hong Kong or whether it comes from China or elsewhere, you know, we really need to be heading towards a hydrogen economy. We need to be generating hydrogen, producing hydrogen, transporting that hydrogen to where it's needed, and we need to replace the fossil fuel that we're using today with that hydrogen fuel.
Yeah, the other question would be on the stability, because when the wind is too gustly, or if it is too slow, you can't turn on the wind turbine. So for cases like Hong Kong or places that are along the sea coast, how much or how should we rely on this, or what is the stability of this wind energy source?
Yeah, you're absolutely right. You know, that's been one of the drawbacks in the past for renewable energy, because it is an intermittent source, and it really does depend when the sun shines and when the wind blows. But with technology in batteries, and as well as hydrogen, again, hydrogen is a storage medium. If you're able to extract the energy when the wind is blowing more than you need, you can reserve that power either in a battery or in a hydrogen fuel cell or as a hydrogen fuel. then you can use it again later when the wind is not blowing. So I think it's really an integration of the offshore wind systems with storage type systems in order to balance out that the problems that you've just highlighted.
Yeah, so remaining on the topic of achieving net zero, let's see if Firas or José, do you have any sharings from the different parts of the world of where you are? Maybe José, do you have any sharings from Portugal about? Okay, let me move on. The
If you
Firas,
allow me,
yeah?
yeah, just it's not a share. I just from time to time when discussing this locally here in Beirut, we hear sometimes about challenges for wind farms and probably issues related to environmental impact assessments. I would like to hear that. Is there any impact or a major impact on the environment, on the marine life, on the birds' life for such wind farms?
Yeah, well, there can be. I mean, that's the reason for doing the environmental impact assessment. Things like migratory bird routes. You need to be careful because the birds don't necessarily know that you've just built a wind farm there. So if you are building a wind farm in an area where migratory birds travel quite frequently, then it's something that you'd need to be very cognizant of and could even steer you away from a particular site because environmentally it wouldn't be a sound idea. In terms of sort of fish life, I think temporarily there are impacts obviously during the construction of the wind farms, but from my understanding, a lot of the sea creatures, once it's built, actually love the wind farms. I mean, they're great places for sort of breeding and shelter and those sort of things. So in terms of the effect on fish itself, I would say it's probably less so, but maybe on the marine mammals, things like whales and dolphins, you need to be a bit careful. You need to make sure that you're not close to sort of breeding areas because some of these wind farms can be quite noisy. They can put vibrations in the water. And therefore, again, needs to be considered. So it is an important aspect. It is something you need to look at the very beginning of a project. It's something that we would try to avoid. And if we can't avoid, we would try and mitigate as much as possible to ensure that the impact of the wind farm was minimized as far as possible.
Yes, indeed. So environmental aspects, we need to strike a balance as well. The other question would be on the cost, because it can be quite costly to build wind farms offshore. But Peter, you also shared with us the dropping of the cost or the cost of wind energy per unit compared to other energy sources, and it is quite competitive in that sense. But still, do we expect to, or what ways we can drive the technology, the construction technology, such that we can drive down the cost in the future, do you think?
I think it all comes down to the local supply chain. I think as turbines get bigger, they're more efficient. Obviously, the bigger the turbine, the less number of foundations you need. The more efficient the turbines become as the technology improves, and therefore the more wind energy one can capture. So although the capital cost of wind farms is quite expensive, you need to realize that the fuel that drives these turbines is free. I mean, it comes from the wind, and therefore overall, when you look at it over a 25-year life cycle and you compare it against other means of power generation such as coal or gas-fired solutions, then actually they can become, or they have become, as economic as those types of system. So I believe there is a strong case now for the development and more rapid development of these types of system.
So with the originally quite low in the operational cost, to further drive down cost would be on the capital investment and how we can drive down in that aspect. The other thing would be the grid stability, and also with the introduction of feed-in tariffs, so which is quite common in areas such as Japan or Germany. And do you think that can be applied in regions such as Hong Kong, and also Hong Kong integrating its energy network, the grid with mainland China?
Yes, certainly. I mean, feed-in tariffs are important, I think, because they're usually required at the beginning of a market. So it's usually a market where there is no established supply chain. So you need government investment in order to encourage the developers and be able to subsidize those developers to enable them to construct the early wind farms. And once you construct the early wind farms, you do develop that supply chain, and therefore the need for feed-in tariffs reduces over time. I don't think they're sustainable forever. You know, it just needs to be enough to get that development created. And then as time goes on, as you can see in Europe, they're actually getting to the point where feed-in tariffs are no longer required, and they're actually competitive with other fuels. So that should really be the target for all markets.
Yeah, the other thing that we've read from the news in the last week, in fact, is about the hydropower in mainland China, with the drought that has happened in the last week along the upstream of the Yangtze River. So that has switched off all the majority of the hydropower station. Do we expect to see something similar in terms of in the wind energy sector, and how we can mitigate or prevent such problem from happening?
I wouldn't have said it's the same problem. I mean, I think with hydropower, you're relying on rainfall, which is quite unpredictable. You can't always encourage the rain to fall where you need it to fall. But I think with offshore wind, wind is always going to be there. It's generated by weather patterns which have been ongoing for millennia, basically. So essentially, I can't see the wind ever stopping to be there.
Yeah, okay. I think that's has cleared all the questions from the chat box. Let's see if we have any final questions from the panelists or our audience tonight. Or let's see if there's any final remarks from Firas or Joseph or Peter.
Yes, I have a final remark. Just to congratulate Peter Thompson for this very comprehensive and excellent presentation and discussion. Thank you very much. And also to congratulate our committee of young engineers and future leaders, Firas and Tang. You are in a very, very good shape. So please continue with this work, because it's very important for WFEO and for attracting more young people from to the engineering sector. So this is, as we see, a very important issue for the development of humanity. Energy is very, very important, and these renewable types of energy are very interesting for the research and practice of engineers in constructing a more sustainable world. Thank you very much.
Okay, thank you very much. Thank you once again for our panelists and our speaker, Peter, and also all the audience, and have a nice day wherever you are in the world. Thank you.